Can you hear me?
Yes, perfect.
Okay.
All right. So sorry about that delay. The poster session was running a bit long. So our next keynote talk is going to be by Hyun Myung with a talk titled Spatial AI and ML for Autonomous Robot Navigation in Rough Terrains. Professor Hyun Myung is a full professor in the School of Electrical Engineering at KAIST. He has won several awards, including first place in ICRA 2023 QRC, which is the Quadruped Robot Challenge, first place in ICRA 2025 NSS, or Nothing Stands Still Challenge, first place in ICRA 2023 Hilti Slam Challenge LiDAR Session, CES 2023 Innovation Award, the 2022 IEEE RAL Best Paper Award. His current research interests include autonomous robot navigation, SLAM, spatial AI and ML, and swarm robots.
Thanks for your introduction. I guess you can hear me. So hello, everyone. It's my great honor to share our recent development in this workshop. And I'm also sorry to attend online due to my schedule. Okay. So let me first talk about spatial AI for autonomous robot navigation and autonomous navigation of the leg robots and conclusion. So as you already know, the core technologies of autonomous robot navigation consists of mapping, localization, and motion control. And among them, doing the mapping and localization at the same time is called SLAM. Our core technology for spatial AI is as follows. In the control part, we have developed deep reinforcement learning-based blind locomotion controller called DreamWork. And in the SLAM part, we are focusing on the dynamic and feature pro environment. So for dealing with the dynamic environment, we have developed the DynaBeans. And for dealing with the feature pro environment, we have developed Adaleo and UV Slam. And recently, our team won the first place in NSS Challenge, which deals with the multi-session SLAM problem. And for leg lobos, we have developed the STEP algorithm. And in the planning part, traversable area detection algorithm called Travel has been developed. TRG planner and the Peacock planner for the global and local path planning, respectively. And for dynamic object tracking and removal, we have developed the toss and erasure algorithms. In more detail, we are focusing on the graph-based SLAM for dealing with the dynamic and feature pro environment. For dealing with the dynamic environment, DynaBeans and DynaBeans++ have been proposed. And for dealing with the feature pro environment, we have developed Adaleo and the UV Slam. In the ICRA 23 Hilti Slam Challenge, we got the first place in LiDAR session and the second place in the vision session. In the dynamic environment, we can detect dynamic objects using deep learning and remove them in the feature set. But for untrained classes, we cannot deal with them properly. So we have proposed DynaBeans to deal with the dynamic object, not using the deep learning. So as you can see in this video, our algorithm can discriminate dynamic features from the static features. And even when the truck is covering most of the scenes, DynaBeans performs best compared to the other SOTA algorithms like Beans Fusion or ORB Slam 3 and DynaSlam. For LiDAR-based SLAM, we have developed Adaleo, and this is the acronym for Adaptive LiDAR Inertial Odometry. The SOTA algorithm, like faster Leo, diverges in narrow spaces because the number of point data is decreased in the case. But our algorithm Adaleo can adaptively maintain the number of point data in a voxel regardless of the area size. So we have two novel approaches for that. At first, Adaleo employs an adaptive parameter strategy. After checking the degeneracy, we adaptively change the parameters to maintain constant number of points in a voxel. As a result, while faster Leo diverges in narrow spaces, Adder layer is very robust in the localization performance. So as you can see in this video, if we pass through some narrow spaces like the corridors or the stairs, the faster layer diverges while our algorithm maintains its course. Second, we have focused on a robust loop closing. The ICP variants like GICP are still widely used, but these are local registration methods. So they only succeed if the pose difference between the source and target clouds are small. The problem is that if the pose differences goes further, the loop closing usually fails. So there is also a sparsity issue due to the nature of the 3D LiDAR, leading to the degradation of the feature matching performance. So we have proposed COTRO to deal with this problem. Assuming we have a ground vehicle, we only estimate X, Y, Z, and yaw for going roll and pitch angles. So using max click, inlier selection, and component-wise translation estimation, COTRO shows robustness despite large pose discrepancy. We also have tested whether the performance of grab slam can be actually improved when our proposed method is used as a course alignment. As you can see in this figure, COTRO applied slam shows the best performance. COTRO++ is a recent improvement over COTRO. So we first segment ground by the patchwork algorithm. After then, FPFH feature extraction algorithm is applied on both the source and target clouds. After descriptor matching, COTRO is applied to get the final result. So in the small loop cases, both algorithms successfully perform loop closing very well. But in the large scale loop, like in this case, COTRO++ minimizes the outliers and performs better than the original Ligoroam algorithm, resulting in a more precise map like this. You can compare the maps created by both methods. We have recently developed a robust LiDAR inertial odometry using smooth IMU propagation in SE3 manifold. While most previous methods, such as fast Leo and Bin's mono, have presented the 6DOF pose by rotation and position separately, we represent the pose by transformation matrix that lies on SE3 manifold. In addition, we jointly predict the rotation and position of on the tangent space of the manifold during the IMU propagation. By doing so, as you can see in this figure, position deviation can reflect the rotation changes, while existing methods cannot, as they only predict the rotation and position separately. Therefore, our method enables smoother and more accurate IMU propagation. We evaluate our method on a large scale off-road environment using the UGV platform like this. So our method achieved accurate pose estimation in such rough terrain, as you can see in this figure. So we have compared our odometry with the RTK GPS, and they actually coincide very well. And after traversal, if we revisit the origin, then there is a very small pose discrepancy, as you can see. So you can check it in this video also. So vehicle traverses like this way and gets to the starting point, and we have very little pose discrepancy, as you can see. So we also have evaluated our method across various rough terrains, such as disaster robotics center, which features gravel, sand, and steep stairs, and also muddy orchard and a sloped park with the steep slopes at KAIST campus, and ICRA 24 QRC competition site. So across all these challenging environments, our method demonstrated robust and accurate performance. As you can check it by this consistent map. Lastly, we tested our algorithm on a challenging drone dataset. So this dataset includes aggressive drone motion with rapid heading changes and sparse LiDAR point clouds. Even under such difficult conditions, our method showed high accuracy with very little drift compared with Fast Rio 2. So you can check it by the shape of the load and also the shape of the building. Okay. And for the visual SLAM, we have proposed UV SLAM, unconstrained line-based SLAM using vanishing points for structural mapping. So the vanishing point factor selects the lines with the same vanishing points, which is quite effective in the aligned feature extraction. By using the vanishing point factor, we could make feature information matrix full length. That means the states are fully observable. This UV SLAM can be run in our smartphones. Using only the images and the IMU data, we can robustly track the poses in the smartphones. So we can have some AR applications like this. And this is the third floor in a building, and we can come down through the stairs and second floor like this way. The NSS challenge was held in ICRA 25. The objective is to build a 4D map of the construction site using LiDAR scans at different times, as indicated by different colors in this figure. As you can see in this construction site video, the scans are very dynamic. Sometimes some things are created and some things disappear, so the scans are continuously changing over time. So we have to register all those scans with no prior information on their acquired poses. To solve this problem, we have developed a dedicated multi-session SLAM algorithm. At the core of the solution was a multi-way registration method designed to align LiDAR scans across multiple sessions without prior connectivity. The system integrates three modules: cubic fit. This is the neural net for local feature summarization and correspondence extraction. And Quattro, this is a global registration algorithm. And finally, Chameleon, the refined module based on the change detection neural net. So after all, our team recorded a global RMSE of just 0.28 meters, outperforming the second and third place teams by an order of magnitude. So this remarkable result reflects both the precision and robustness of our approach to mapping dynamic construction environments over time. Next, let me talk about autonomous navigation of the legged robots. We have developed the VIO algorithm for quadrupedal robot, and it is called the STEP. We use the pre-integrated foot velocity factor added to the Vince fusion graph and utilize leg kinematics without non-slip assumption to deal with the slippery condition. The conventional non-slip assumption is vulnerable to slippage. So we relaxed this assumption by estimating the foot velocity and put it in the cost function to be optimized. By doing so, STEP algorithm shows superior performance in slippery and rough terrain compared with other SOTA algorithms like Prontor and Vince fusion. And to deal with the situation under insufficient visual information, we have developed Deep STEP. We improved the performance of the STEP utilizing the inertial joint network that influences the outputs, the relative position from proprioceptive sensors like IMU, and the joint sensors. So the outputs from the step and the joint inertial networks are fused together and using the attention-based ray fusion algorithm like this. And as you can see in this video, Deep Step robustly estimates the position after a roof, even when the camera suffers from illumination changes. In contrast, Vince Fusion and Step are more vulnerable to illumination changes. In section A, the weight of the step is small because of the low image intensity, while in sections B and C, the step had a larger weight due to the moderate intensity condition. So you can show that they are fused quite well. We have developed LVIQ, which is the LiDAR Visual Inertial Kinematic Odometry. This incorporates alternating optimization between the visual and the LiDAR odometry. So LICO, which is the LiDAR Inertial Kinematic Odometry, this incorporates lag kinematics with the point-to-plane optimization. And BICO module, this exploits the lag kinematics and robust LiDAR visual depth association along with the visual feature tracking pipeline. You can see that the localization accuracy is good when the robot steps down the stairs in this rough terrain. In this video, you can see the LiDAR visual depth association using spot pixel clusters on top of the visual feature tracking. When the legged robots works, we have to detect the traversable area. So we have developed the traversable area detection algorithm called the Travel. This algorithm segments traversable ground and above ground objects using graph representation of the 3D LiDAR scans. And green points indicates the traversable area, while the other colors indicate the clustered above ground objects. We further enhanced the travel algorithm to TRIP, which is a terrain traversability mapping algorithm. So we can obtain the terrain map for enhanced robot locomotion performance, and the traversability and the risk maps are obtained for enhanced autonomous navigation capabilities. To obtain the static map, we have developed a 3D LiDAR-based dynamic object segmentation algorithm called TOS. The traversability-based object segmentation module uses the travel and 3D multi-object tracking-based dynamic object detection module outputs coarse classification of the dynamic and the static objects. After that, we apply the DS boarding, which defines the dynamic objects based on a boarding scheme. You can see that the dynamic objects are identified and tracked in real time. And the trails of the moving dynamic humans are identified and can be erased to get a static map. So we don't have the post-processing. All these processes are done in real time. This shows the overall real-time 3D spatial AI framework. LVIQ and Travel and TOS, they are utilized to get a static global map and localize the robot in real time. In the field test done at the KAIST campus, the robot traveled about 1.2 kilometers and we got the RPE of 20 centimeters, which is a pretty good accuracy. For commercial quadrupedal robots, usually the robot's built-in controller requires the user to manually change the walking mode for traversing different terrains such as the stairs. So when this mode is not enabled, the robot will quickly fail to traverse through these rough terrains. This is because the conventional NPC requires the accurate map and the robot model in advance. So to deal with this problem, we have developed a blind locomotion controller called the DreamWalk. So we employ the robust blind locomotion policy learning by your asymmetric actor critic. And for the context-aided estimator, we have designed this one, and this will estimate the latent representation of the surrounding terrain. This CENet estimates the robot body velocity and the latent context vector GT at the same time. And without this context vector, the estimator fails to accurately estimate robot body velocity during stumble. So all this training is done in the simulation. It takes about an hour for training if we are using NVIDIA 3060 Ti. So DreamWorks can be applied to some larger platforms like Hound 2, which was developed at KAIST.
The sun was shining, the geese were waddling, and so we took the Hound out for a walk around campus to learn about another kind of technology being developed by KAIST's Urban Robotics Lab. The Hound has been programmed with a new software called DreamWalk. This enables blind locomotion, meaning the robot can navigate uneven terrain with no camera or LiDAR sensors to see where it's going. Like on the racetrack, it's getting basic instructions like stop and go from a controller, but it has to feel out and adapt to the terrain for each step it takes. This is the accumulation of knowledge and data taken from 4,000 virtual robots learning to walk at the same time.
So after 1 hour of training in the Isaac gym simulator, the robot could successfully climb up the stairs. So we were also very surprised by this rapid adaptability of the DreamWalk. We also developed a fall recovery function called the DreamLizer. By dropping the robots in various poses in discrete environment, we could successfully train the robot to stand up quickly after its fall. And other skills are also possible. So what if we change the pose tracking reward into a different body orientation reward? So interestingly, the robot can run a handstand motion as shown here. And also the hind legs standing motion. And lastly, it shows the retrying behavior when the robot fails to stand up, which is an emergent behavior. So with all our technologies, we participated in ICRA 23 QRC quadrupedal robot challenges, which was held in London, UK. There are 5 sections, A, B, C, D, E, with a total of 10 by 20 meters in size. All these sections actually mimic the disaster situations, such as the slanted concretes with dust after collapse, and sand, mud, and puddle, and step and holes, which makes the wheels and caterpillars impossible to navigate these terrains. So in the easy setting, we can get 1 point using teleoperation, and we can get 4 points using autonomous navigation. For harder settings, we can get the double points of the easy settings. So 6 teams battled in the final, and we got the first place. So only 2 teams, KAIST and IIT from Italy, performed autonomous navigation, while the other teams only performed teleoperation. You can see some of the videos for the details of the QRC. Yeah, this shows the 5 sections. We use the 3D LiDAR and the camera for exteroceptive sensors, and joint and IMU for proprioceptive sensors. We have compared the FastLEO with our algorithm LVIK. This is the extension of the LEO, which incorporates the kinematic data also. Okay, this also shows the deep step algorithm. So even in the dark situation, we can cope with the localization problem. And this shows the terrain mapping algorithm. We can get the height map as well as the risk maps. And using this risk graph, we can plan the paths. So the colors in these edges indicates the risks. So the whiter area shows the safe area. So we first plan the global paths, and then when traversing, we also use the local planner, as you can see. So it uses multiple candidates, and one of them will be selected to avoid the obstacle, and the most energy efficient one will be selected. Okay. So this shows the overall framework of our dream step algorithm. Adder this is the extension of the adder with the kinematic constraint like step. And Quattro was used for loop closing, and TOS was used for static map generation. And Travel was used as a terrain mapper. TRG planner was used as the global planner, and the Pico planner was used for the local planner. And DreamWork was used as a locomotion controller. In the real competition, some of the components were modified for real-time performance. So for the global path planner, we have developed TRG planner, traversable risk graph-based path planner. Since the risk of the terrain should be considered in rough terrains, we proposed traversable risk graph to represent the risks of the path candidates and optimize the path using this information. Because the 3D graph structure is generated very fast, we can utilize this TRG planner even when we don't have the prior map. And we can also replan the path when there are dynamic objects in front. So if you are interested in more details, please refer to the IEEE RAM September issue in 2023. So our team's screenshot was depicted here. We also have developed a fault-aware quadrupedal locomotion controller called DreamFlex. In this video, the failure actually occurred in the right front leg during the walking experiment in the outdoor. And despite this, the controller was able to identify the failure joint in real time and adaptively change the gait pattern to successfully work stably using the other three legs. This controller is a small modification from our DreamWork. We use the fault vector, and using this fault vector, we can estimate the fault joint. Recently, we have developed DreamWork Plus, which is an extension of the DreamWork. We use the exteroceptive scan dots for terrain reconstruction like this. This enables more agile and non-colliding locomotion. This shows the details of the DreamWork Plus, which is more complicated than DreamWork, but also runs in real time. The front robot is controlled by DreamWork and the other two robots are controlled by DreamWorks. You can see that the front robot runs faster and does not collide with the steps, which was frequent in DreamWorks. And also 15 centimeter stairs can be overcome, though the specification of the Unity Go 1 is 10 centimeters stairs. And also probing behavior is quite interesting. Though we have commanded the robot to go forward, it retreats and tries to see beyond the cliff to jump. And the last video shows that DreamWorks++ controls the robot to be aligned with the slope, while DreamWorks could not. Our team recently made this portable mapper for easy reconstruction of the 3D maps. If we install this portable mapper to the legged robots, it turns to the autonomous legged robots. If you install the portable mapper to the wheeled robot, it turns to the autonomous ground vehicle. So we have tested the mapper to detect the changes in the map, as you can see in this video. The orange colored points cloud indicates the changed points. Like this way, you can quickly detect the changes from this environment. On this video, you can see that the robot autonomously navigate and have some poses to capture the gauge information at that point. So in the future, we hope we can replace the human labor by this auto inspection robot. Our robot shows very agile and robust locomotion in rough terrains and can be applied to various robot platforms like Animal C, and Mini Cheetah, and so on. And even the humanoid robots can be controlled by our blind locomotion controller, as you can see. Using only the IMU and the joint sensor information, we can have this locomotion behavior. B2Wheel, this is the wheel-legged robot, and this can be also trained by our DreamWorks. We can command the robot to go forward, but the robot can determine when to use the legs or wheels autonomously. Yeah, like this way. And also in the stair environment, it navigates using its legs on the stairs and wheels on the flat terrain. So this shows the generalization capability of our DreamWorks controller. Recently, we are adopting VLMs to our controller. Local VLM, this is the first work to demonstrate the real-time adaptation of the legged locomotion using high-level reasoning from environmental semantics. From LLMs, we extract the skill set database offline because LLMs do not provide a constant latency. Then with a VLM, we extract the motion descriptor, mixed precision, and finally style conditioned locomotion policy is outputted in real time. So with the language command or image perception, we can show the autonomously generated locomotion like this. Trotting around, or if the robot perceives the baby is sleeping, then it shows very slow locomotion like this. Show me a rabbit. Frog. Dance for me. So we have not programmed this kind of behavior. So this behavior is generated autonomously by using LLMs and VLMs. So in conclusion, in the near future, VLMs and LLMs can be utilized for incorporating the common sense to our previous methods. And this video shows the morbot, which can excavate underground, and the drone called Carlos H. They can fly and perch to the wall. And in the near future, we will apply our autonomy stacks to these new robot platforms made by our lab. There are many applications like space exploration also. Thanks for your kind attention.